Good morning. This video I'm doing in some small parts. I don't know how many I will be doing. The object is to see what we can conclude from a formula like this about the number fields, getting the value of the L function from the sum of or from the coefficients of theta 5. So that's the number of ways different numbers can be written as the sum of 5 squares. I've had to go through a lot of the previous theory and check that my results were right. And one thing that confused me was that here on page 181, they use another notation than they did in problem 2 of section 3.3, where we computed the ramification indices h. So what I've done is I've verified this result, and then this was silly because you just have to put that into an odd power, so we can start squaring it. That gives 2i divided by 4. That's I halves. And now if we write k as 2 lambda plus 1, then we get I halves, I halves to lambda times 1 plus I. Isn't that divided by 2? Yes, it is. Divided by 2 to kth. This is 2 to, it's 2 to lambda plus 1. So that was wrong. So that's the first part of getting the coefficients right. I have to correct them. I won't waste your time, I'll just write the result. Hello, Saturday afternoon, reporting on the results regarding the values of the L functions. Having established this, the next step was to compute the constants before the L functions. And adding them, I got this. This guy is unknown. We know before, because that formula was derived, but the formulas for L naught times 4 to some power was not in the book. It just stated that that was complicated. We'll see about that. And adding up and comparing the result of capital theta. I actually verified that combinatorically because I thought that was a strange number. All right, you see, I thought from here, this value is -1, this is -2, so I thought maybe they should be integers, all of them. So I thought there was a mistake here. I realized that this would give us the value of the positive, the value of the L function at 2. And we might be able to sum that directly. So I went to Mabel, and it didn't know the sums. Yeah, I could ask it to do it numerically, of course, but then I realized that the sum for one of them, all the 8n plus 1s, that can be expressed in the translated theta function, which apparently here is called capital psi, capital psi. So maybe it might be able to reduce it if I did it that way. So that's what I did. First, with chi2, the coefficients are 1, -1, -1, 1. I just took them out. It has conductor 8, as you see. Hooray! It actually knew the result. Excellent. And then we could compute the value of the L function at -1, which turned out to be -1. Success. The same will L3 of chi at 2. I did the same, found out where we had non-zero values of the of chi, or chi3 of n. Hooray! And L5, it produced this result, which is annoying because it's very easy to simplify. If you take this outside parenthesis, then it's 1 minus square root 5. I wanted to get Maple to do that, so I found out to use rationalize, which gives a rational denominator, or rather an integer denominator. And then I got this and asked it to expand, and finally, hooray, we got the result. And from this we can compute the value of -1 to get -2/5, and I just had to do this. Of course, this gives 56, so it's not so difficult. But I couldn't do it in my head by then. All right, so let's get back to Paris and check the values of the for instance, L2. 8723580249548599410. Oh, so here one of them starts getting it wrong. Well, that's about it. Studying this section, I have two outstanding problems. The first problem is deriving the formulas for AL, which is, I tried to do it, so it is difficult, but maybe I'm just missing a trick. The next problem is the character chi m, which expands m over j for j odd. So it vanishes when j is even and m is even, and I haven't verified that that's the only possibility given the right conductor. So that's our two outstanding problems, and I'll just carry on with those unsolved.